Good afternoon, everyone. My friend Jenna here just gave us a very nice introduction on how we can use sunlight to generate electricity. Now I'm going to tell you a different approach to utilize solar energy, which is to use sunlight to perform chemical transformations. My name is Shichen Lian. I am a chemistry PhD student here at Northwestern University. Here I show you 4 molecules. Each of these molecules is held together by a form of force called a chemical bond. If you look at these molecules, you can tell they only have 4 different atoms: carbon, oxygen, nitrogen, and hydrogen. By rearranging these 4 different atoms, which is a process of making and breaking these existing chemical bonds, we can actually make many different kinds of molecules, such as glucose, which is a form of sugar, or something more complicated like this, which is a type of antibacterial drug. In nature, there is actually a very efficient example to perform this kind of chemical transformation by using sunlight, which is called photosynthesis. Plants can absorb sunlight and transfer this absorbed solar energy into a place called a reaction center, where carbon dioxide and water will react to form glucose and oxygen. So as a chemist, we are always curious finding the most efficient way to make and break chemical bonds to do this kind of chemical transformations. If we look at this very simple example, converting carbon dioxide, which is a very harmful greenhouse gas, into carbon monoxide, which is a potentially useful chemical fuel. From a chemical perspective, we have to start from our starting material, which is carbon dioxide. And we have to go through an intermediate state in order to reach our final product. So from this picture, it's very clear that we have to input this amount of energy in order to drive this chemical transformation. And it'll be nice if we can actually utilize sunlight to do so. So in order to use this mechanism, we have to have a very good light absorber to absorb sunlight. And then we have to have a very efficient reaction center to utilize this amount of absorbed solar energy to do this chemical reaction. So in particular, I work with a type of material called semiconductor nanoparticles. Here I show you a figure to help us better understand how small these nanoparticles are. They are about 10 to 100 nanometer in size. If you grab a piece of paper and write a period on it, it's actually about 100,000 times bigger than a nanoparticle. Here is what they actually looks like. You can see from this picture, they are spherical, and the scale bar on the right bottom is about 20 nanometer. So you can see this nanoparticle is about 10 nanometer in diameter. The reason why these nanoparticles are very good, very efficient light absorbers for this kind of applications is because they can absorb different colors of light. As we know, sunlight, at least within the visible region, they have different colors. So if we want to utilize sunlight to perform this kind of chemical transformation, the light absorbers have to absorb all different kinds of light. Here, the picture on the right, I show you some nanoparticles in solution. All of these vials have the same nanoparticles. They have the same chemical composition. The only difference is that the vial on the right is actually bigger than the vial on the blue. So if I want to design a system where these nanoparticles can absorb as much sunlight as possible, I can simply just make the same material and change their size, and I can achieve this goal instead of designing and making something entirely different. Besides this advantage, nanoparticles also have large surface area. Like I mentioned earlier, in order to utilize this kind of mechanism to perform chemical transformation, not only the light absorber has to efficiently absorb sunlight, they also have to transfer this amount of absorbed solar energy into reaction centers. Because nanoparticles have very large surface area, it enables a very close interaction between the light absorber and reaction center. Because of these close interactions, it ensured the efficient delivery of sunlight into reaction center where the actual reaction happens. Here I show you a picture, a schematic of the actual system that I work with in the laboratory. So here I couple a nanoparticle with a reaction center molecule that is active for converting carbon dioxide to carbon monoxide. And then I shine light on this nanoparticle. This nanoparticle absorbs sunlight, transfers the absorbed solar energy to the reaction center, where the carbon dioxide will be converted into carbon monoxide. Thanks to this funding agency, I was able to develop this system simply putting this mixture into a vial, and I can use sunlight as the only energy input to convert this very harmful greenhouse gas carbon dioxide into a potentially useful fuel, carbon monoxide. Thank you for your attention.